First of all, does anyone know what is endometriosis? No? Yeah, one person, of course. But it's perfect because it is a pretext to make some math. So the endometer is a substance that grows inside the uterus, and actually it's not dangerous. It's not dangerous because it is expelled every month during the periods of these ladies. But what is very dangerous is when the endometer grows outside the uterus. So for instance, on the ovaries, on the uterosacral ligaments, the colon, well, everywhere around the uterus. And when it happens, it's very painful, and the only way to cure it is to use surgery. This is a disease, the endometriosis is a disease that happens to approximately 10% of women. If a surgery is needed, it's very important to detect where are the endometers. Otherwise, there is a risk of opening on the wrong side, and after that, you'll just open the people for nothing. So there are two methods to discover where the endometers are. There is the MRI, which is a method in which you just take like a picture of all the abdomen, and you have different slices at different depth in the abdomen. It's here you can see that the image have a good resolution, but it's quite costly, and you have to wait a lot of time before you accede to the machine. Another method is here the TVUS. Basically, you use a probe, you put it into the vagina, and you just look at the tissues all around, and you can observe that here on that picture, the resolution is less good, but you can see somewhere where are the endometers. And when you use both methods, you can just see, okay, with TVUS, you can see there, okay, I have an endometer there, so it's there that I have to look inside my MRI volume. And a question that can be asked is, can we merge both techniques, like look at the endometers like on TVUS, but with good images as in the MRI? And the second question is, okay, if I have to make a surgery, I'd like to know what is the size of the cyst and its depth. To answer the, to answer the first question, which is, can we look inside the vagina with a good image? Actually, it can be a problem of interpolation on AC3. If you record with your probe the orientation of the probe, so here it's a Klein bottle, but you see there is an orientation, and its position during the navigation, you can reconstruct the whole path given some little data. If you have the direction and the position, you can intersect the MRI volume with the plane, which is defined by the orientation of the probe. So like this, you can observe on TVUS, see, okay, I have seen this, and after you have an MRI, you can just show exactly the same path and say, okay, here I had seen an endometer, I think it's an endometer, and on the MRI, I see, okay, it's really an endometer. And to answer the second question, which is, can we evaluate the size of the endometer? You just ask an expert to take different slices at different depth in the MRI volume. He segments the endometer, and given this data, you can reconstruct, here on the right for you, you can reconstruct the cyst. All of this leads to a question, and this question is, how to interpolate on manifolds. So to do so, there are different techniques. There is a geodesic, piecewise geodesic methods. There are Neville's algorithm, but here we are interested in Bézier functions, because Bézier functions intrinsically interpolate two consecutive interpolation points. So here the interpolation points are in red, and in green you have control points which attract the curve, like in Photoshop when you want to draw a path. So here there are 3 segments of Bezier function. So we are going to make a piecewise Bezier function. And why is it useful? It's because it's very easy to compute and even easy to generalize to manifolds. Okay, how do we construct a Bezier function? Here, let's go into the Euclidean space. You have 2 interpolation points in black and 1 here in the middle, which is a control point. The curve is parameterized between 0 and 1. And the algorithm, the de Castelio algorithm, can return you the position on the Bezier curve at a certain time step. So here, for the example, we're going to evaluate it at 1/4, 1/2, and 3/4. The idea is you compute a straight line between 2 consecutive points, and you evaluate the position on that line at the point you want to evaluate your curve. So here, 1/4. Here, the first step is finished. With these 2 points, you draw a straight line, and you evaluate it at 1/4. And believe me or not, this is the position of the Bezier function at 1/4. If you do the same for a lot of points, here 1/2 or 3/4, you do it for a nice discretization of the time, and you obtain the whole curve. And it's very easy to generalize this to manifolds because, as you know, the straight lines is generalized by a geodesics, and if you do the same, you do exactly the same algorithm with geodesics, you can have a curve on manifolds like this. So here the manifold is a sphere. As you may see, there are 4 interpolation points, 4 control points, and the curve stays on the sphere. Well, the problem with the piecewise geodesics is that it's not differentiable at the interpolation points. And here, what we see is, even with Bezier, it's not differentiable. So actually, the question is, how can we make it smooth? So again, let's go back into the Euclidean space. We have different interpolation points, and we'd like to find the position of the control points which are optimal in a certain sense. Here we have decided to say that the extreme segments are quadratic Bezier functions, and the inner segments are a cubic Bezier function, such that each inner interpolation point has a control point on the left and the right. So the conditions for continuity and differentiability are that the velocity on the left and on the right of an inner interpolation points are the same. And it turns out that actually this condition says that the 2 control points on the left and on the right of certain interpolation points must be on the same straight line. So the interpolation points is at the middle of the straight line between the 2 control points. Okay, so here, yeah. Here, this interpolation point must be in the middle of these 2 control points in a sense of a straight line. So on geodesics, it will be on the middle, on manifolds, it will be on the middle of a geodesics. So we can express every point here on the right of the interpolation points are as a function of the interpolation points here and the control point on the left. So with this condition now, we'd like to minimize something. So this is one of the only 2 slides with a lot of mathematics. So we are going to minimize the mean square acceleration of the path. So here you have the first segment. Here you have all the segments inside the interpolation points. And here is the extreme segment at the end of the path. This is a quadratic function in the control points on the left of the interpolation point. So we can derive it, and this gives a linear system here with the unknown, which are b's, and the big vector here is actually a linear combination of interpolation points. As we are on the Euclidean space, it's easy to solve. So the variables are easy to find. We just inverse A, and we obtain that each control point is a convex combination of the interpolation points there. Here is just a result. So you see that on the Euclidean space, hopefully it works. Yeah. So here you see that the velocity is continuous. So we reach the C1 condition, and the acceleration is not. Here you see that the acceleration is constant there. It doesn't work anymore because it's a quadratic Bézier function. And you see also that the control points are and the interpolation points are in the same lines. Now, how do we generalize this to manifolds? So this is, just to recall, this is the way to express the control points in the Euclidean space. And this result, actually, the position of the control points is invariant if you just translate all the problem. So you can say, okay, I will translate my problem given a certain reference point. And the idea to pass to the manifold settings is say, okay, this difference here, this difference here is actually the expression of the logarithm on the Euclidean space. So given a reference point, you just actually project all your points on the tangent space of a given reference point. And you can use the same reference point for the whole problem, or you can just look at it locally and say, okay, for a certain beta I, I'd like to project it on the tangent space of the closest interpolation point. Okay, so it brings us back to the first problem. Was it possible to make an interpolation on AC3? Well, actually, this is the result that we got. So you have here, so the first one there, here is a landmark, this one is a landmark, this one too, this one too, and this one too. And we can reconstruct the whole path of the probe given some landmarks recorded during the navigation. And so, as I said, if you have the orientation, the position of the probe within the AC3, you can intersect it with the MRI volume, and you can see on the MRI what you have seen on the TVUS. And concerning the second application, which is the reconstruction of the endometrial volume, here the manifold is a shape manifold. So an expert just segments different, the endometer on different slices inside the MRI volume. So you have this data set, and you reconstruct the volume here. And as you may see here, this is the velocity. The velocity still is continuous, and here the acceleration is not. So in conclusion, I think I'm in time. Yep. In conclusion, we propose actually, it's not a new way to cure the endometriosis, but it's just a mathematical method to help in medical imaging. It's a generalized C1 interpolative method on manifolds. And as we are using Bézier function, it's quite light because to store your path, you just have to store your control points. It's very fast because we solve the system on the Euclidean space, and it's general because you just need to have a way to project your data on a tangent space and then map it back to the manifold, and that's it. And of course, a way to make a geodesic or a retraction. Just for perspectives, we are now wondering if it is possible to extend to multidimensional interpolation. For instance, making surfaces of Bézier on manifolds. Actually, it's possible. And we are working on it with Pierre, Antoine, and some guys from Münster. The paper is submitted, but well, it will arrive on archive soon, but it's not done yet. So that's it. Thank you for your attention.
For the reconstruction of the volume, then how do you choose the points in the different slides?
The landmarks there?
Yeah.
Actually, it's an expert that just segments here.
Yes.
Here. You have different slices that an expert chooses. And he sees that, okay, here you can see the endometer, so I can segment it easily. Here I can see it too, here too. So you know at what depth you are in the MRI volume.
But for each depth, do you need to have the same number of the points? On the
Yep. Yes. Yeah. Yes. Here, because each slice is an element of a shape manifold.
Yeah.
So to represent it in a computer.
And so the problem is how to select the points on the different. Different
Actually, I don't know. You just choose, for instance, here. I think here you choose that this is the starting point there, and you have also the same starting point there and there and there. And
there is not any problem of the correspondence between the different.
They shouldn't be normally.
Another great question, maybe? No more question? So thanks again.